Very good morning to all of you. I hope all of you safe in your homes. Okay. Today I want to start module 3 of session 3. Title of module 3 is Stability of Slopes. Course outcome of stability of slopes are given. Ability to estimate factor of safety against failure of slopes. Title of subject is Applied Geotechnical Engineering and subject code is 18CV62 of 6 semesters in civil engineering departments. So today's session 3 contents is stability calculations by friction circle, that is 5 circle methods. Today's most important parameters is this one, and second content is Taylor stability numbers. These two contents are required to explain in detail of today's class. So that's why all of you be silent and listen today's session 3 class with your patience. Okay. Last session we have discussed about stability calculation by Swedish methods and as well as Fellenius methods. Now today I want to explain about how to calculate stability by friction circle method, and next one is by Taylor stability numbers. Okay. See, this is the friction circle methods. Okay. How this friction circle method is applied for given data. Okay. So here see, this is the ground levels, this is the slope, this is the top level of embankments, and this is the height of the embankment, and this is the radius, and this is the slip circles. Okay, and these dotted lines are the friction circles. Okay, and these dotted lines are denoted to locate phi value, and this is the tangential point, this is self weight of the embankment acting downwards, that we are locating as a W, and this line we are calculating in terms of Cm equal to Cm into Lc, and here Cm is nothing but a mobilized cohesion, Lc is nothing but here this is the length of our chord, so this is called chord. Okay, so and this is the lever arm A, this lines, this is lever arm A. Okay, so and this is the radius lines, and in between this line and this line we are selecting this as a theta value. See, this is the theta value, and we are measured in terms of radians, and this radius we are considering as a r sin phi. Small radius of friction circle is r sin phi, and this is we are considering radius as a k times r sin phi. So based on this concept, now how plot this sketch I will explain in details. Okay, so here see, this is the procedure, so I will read out, so then once again I will explain above diagrams. Okay, following procedure is given for drawing friction circle method. Following procedure is given for drawing friction circle method and calculation of factor of safety. Okay. First step, draw the embankment as per given slope. Draw the embankment as per given slope or direction angles. Given slope or direction angles. Okay. So means, see here, draw the horizontal lines and based on the given slope or direction angles you locate the embankments, so with respect to given height of the embankments. Okay. Next, second step, now locate the origin O with a radius R and draw the slip circle from tau towards embankments. So according to this step, see this diagram, now locate O point here and O and this as a radius, okay, and this as a tau point, and you take from here to here this as a radius and draw the slip circles towards embankments. Okay. So this is step number 2. So in step number 3, locate friction circle, that is by taking radius small r equal to r sin phi, where phi equal to angle of internal friction of soil. Angle of internal friction of soil, this is given in problem, soil phi value. So then you take radius into multiply sin phi, we are getting small r distance. So based on this value, now you look at the friction circles. See here, this is the radius r sin phi, O as a center and draw the friction circle in terms of dotted lines. Okay. Next, now once again select a radius equal to k times r sin phi and draw this circle as shown above. Okay. Means now you, this radius k value is given. Okay. So now that is constants is given. So now you, this value as a radius, so from here to here this as a radius and draw the circles once again. Okay. Next, now draw the tangent to the inner circle and this tangent extend up to slip circle pass, up to slip circle pass, and locate this is reaction R dash, this is reaction R dash. So means this, so from this point, okay, now you locate self weight of the embankment at the centers, you locate W and see here, so from this line as a 90 degree. Okay. Now draw the these lines. Okay. Next, now draw the tangent points. So from these circles, okay, this line is perpendicular to these lines. Okay. Now come towards like that, draw this dotted lines. Okay, these two lines are passing to each other. Okay, so then look at the reactions. So this is reaction lines at these points R dash. Okay. Next, now then draw a line from O, join at R1 point and measure the angle. This angle is called friction circle phi. Okay, here O from this point to this point you join. Okay, so now, so this point as a R dash reaction point and you measure these angles in between these two lines. So that is value phi dash, friction circles. Then after knowing phi value, draw the lever arm A that is perpendicular to inner tangent OA at a distance A, and this force is called mobilized cohesive. Means according to this step, see here, this is draw the lever arm. So this lever arm is perpendicular to these tangential points. Okay, make the protector and make parallel to these lines and draw like that. Okay, so passing through these points, so this is tangential force. Okay, this tangential force is perpendicular to lever arm. Okay, so this is parallel to this radius. Okay, and this line we are locating as a cm equal to cm into lc. Okay, next calculate lever arm a equal to L by LC into R, L by LC into R, where L is length of arc, is we are calculating R into theta, where theta is in radians, so means we are multiplying pi by 180, we are getting radians. Okay, after getting L, L means this length of arc means this, so from here to here, this is the length of arc L. Okay, next now we calculate chord length, that is LC equal to 2r times sin phi, 2r times sin theta. Okay, so here theta value is this, so this is theta value. Okay, you measure this theta value. Okay, so after calculating chord length, now you mention radius of slip circle in meters. So this is given, so R is radius of slip circle in meters. So in next step, calculate factor of safety for cohesion. Calculate factor of safety for cohesion is given by factor of safety S equal to C by Cm. The C is the actual cohesion of soil given and Cm is the mobilized cohesion from the above figure. Say this is Cm value. Okay, mobilized cohesion. Okay, next calculate factor of safety for angle of internal friction phi. So means with respect to phi you calculate factor of safety, that is factor of safety equal to tan phi dash by tan phi m. So this is equation number 3 to calculate factor of safety with respect to phi value, where k is, we are selecting as a phi m should be taken. K you take with respect to phi m should be taken, means mobilized angle of internal frictions, means you take this value, this phi value is angle of internal friction of the values. Okay, next, so this is the clear explanation of friction circle methods, how to plot the friction circle and how to calculate the factor of safety with respect to friction circles. Okay, now next part is Taylor stability numbers. How to calculate factor of safety by Taylor stability numbers. How to calculate factor of safety by Taylor stability number. See, this is the finite infinite slope in clay soils. So this is the ground levels of slope and of cutting depth of slope is h, and we are selecting this is one elemental area of slope. Self weight of this slope acting downward, that is W, acting at an angle beta slope. Okay, now look at the resultant forces. Okay, so here sigma v is upward to the self weight of the embankments, and sigma n is the normal force acting at point this, and this is the shear stress tau. Okay, so like if slope is acting downward, shear stress is acting upwards. So means shear is, we have already defined as when two body contact to each other, then when heat produced while moving in opposite direction of the body is called as a shear. So same concept is here. Here self weight of embankment is moving downward, then soil force is acting upwards. So here shear is developed, that is we are locating as a shear stress tau. And based on this concept, we are able to plot shear stress diagrams. Okay, so x-axis is normal stress, y-axis is shear stress scale we are selecting, and based on the C5 value we are locating the failure planes. So this failure plane acting at an angle beta, and this failure plane for C5 value. Okay, now you select, this is A point, this is B point, this is E point, this is D points. Okay, and this coinciding points we are considering as a small c point, and this distance we are taking as a c dash. So this concept you know already, based on stress shear strength parameter, how plot the stress shear stress diagrams. Okay, so now, and this line we are defining as a failure modified failure envelope, and this value we are selecting as a phi dash, and this distance we are selecting as a c dash. From figure 9, so this figure 9, tau equal to c plus sigma phi into tan phi. So this main equations we have already seen in shear strength of soil units. So based on the failure envelope, we have confirmed shear stress equal to c plus sigma tan phi. This is equation number 1. Then now you calculate tau equal to gamma h sin beta into cos beta, and sigma dash is, you consider gamma h into cos square beta. Okay, now you use the equation for calculation of Taylor stability number. Tau equal to gamma h into sin beta into cos beta, and sigma dash equal to gamma h into cos square beta. Next, substituting in equation 1, so like that, Cm dash equal to gamma h cos square beta into tan beta minus tan phi m dash, or stability number Ns equal to Cm dash by gamma h. So now substitute the value in this equation, so that is cos square beta into tan beta minus tan phi m dash, where h is the allowable heights of the embankments. So I mean this allowable height of the embankments. Term Cm dash by gamma h is a dimensionless expression called the Taylor stability number, and is designated as Ns, that is Taylor stability number. The stability number with respect to cohesion is given by, the stability number with respect to cohesion is given by Ns equal to c dash by fc into gamma h, or cos square beta times tan beta minus tan phi dash. This is equation number 2, where Cm dash equal to c dash by fc, based on these equations. So then the stability number in equation 2 is, while substituting, Ns equal to c dash by fc into gamma h, is, we are considering c dash by gamma into hc. This is equation number 3, where hc called critical height, hc called critical height from equation 3. Then factor of safety with respect to cohesions, we have to write hc by h is nothing but a fh. This is equation 4. Factor of safety with respect to cohesion, hc by h. So that's we are locating as a fh, factor of safety with respect to height. Therefore, it indicates that the factor of safety with respect to cohesion, fc, is the same as the factor of safety with respect to height, fh. So these are the explanations and equations are seen to calculate factor of safety by Taylor stability numbers. So here all of you remember how equations are derived and how equations are remembered. So these equations you should be remember, be carefully for explanation of Taylor stability number and for calculation of some problems. These equations are more helpful while solving numerical problems. So up to this, now all theories are over in part 1 of stability of slopes. So now based on this theory, that is session 1 to session 3, after clearing of the basic concept of stability of slopes, how stability is calculated based on the given data, means while seeing the numerical problem, how stability is calculated, that is the next parts. See, this is the first problem of stability of slopes model. A laboratory test gave the following soil parameters: C equal to 40 kN per meter square, phi equal to 30 degree. The expected parameters of the mobilized shearing resistance are C equal to 25 kN per meter square, phi m equal to 22 degree. The average effective pressure on the failure plane is 150 kN per meter square. Find factor of safety with respect to average shearing strength, cohesion and internal friction. So this is the problem asked in this module. Solution: given data, C equal to 40 kN per meter square, phi is given, and phi is 30 degree is given, Cm is 25 kN per meter square is given, phi m dash is 22 degree is given, sigma dash is 150 kN per meter square is given. Next, to find tau f equal to how much? In the second case, factor of safety F equal to how much with respect to cohesion, and factor of safety with respect to angle of internal frictions, Fi equal to how much. So this is the clear given data and what is to be required in these problems. Procedure: shearing strength of soil is given by the following equations. Shearing strength of the soil is given by the following equation: tau f equal to C plus sigma tan phi dash. Shearing strength tau f equal to C plus sigma dash into tan phi. Substitute the value in this equation. C is 40 plus sigma dash is 150 into tan phi is 30. So we are getting answer is 126.60 kN per meter square. This is shearing strength. Next, second step, mobilized shearing strength resistance. Mobilized shearing resistance is given by the following equation, that is tau phi m equal to C plus sigma dash into tan phi m. Substitute the value in this equation. C is 25 plus sigma dash is 150 into phi m is 22 degree. So now after calculation of these equations, we are getting 85.60 kN per meter square. Next step, factor of safety with respect to average shearing strength is given by the equation, that is factor of safety F equal to tau f by tau f m. So now substitute the value here. Tau f is 126.6 divided by tau f m is 85.604. Now we are getting 1.479. This is the factor of safety. Next step, factor of safety with respect to cohesion is given by the equation, that is Fc equal to C by Cm. So here C is 40, Cm is 25. So answer is 1.46. This is factor of safety with respect to cohesion. Factor of safety with respect to friction is given by the equation. factor of safety with respect to friction is given by the equation, that is Fy equal to tan phi by tan phi m. So now in this equation, tan phi is 30 degree and tan phi m is 22 degree. So now while solving this, we are getting factor of safety is 1.429. So this is the solution of this type of problems. Next, an embankment is made of a soil having C equal to 25 kN per meter square and phi is 20 degree, that is angle of shearing resistance, and gamma is 19 kN per cubic meter, that is unit weight. The slope is 1.5 horizontal to 1 vertical and of 9 meter in height. Determine factor of safety along a slip circle passing through the tow. The center of slip circle is located by directional angles alpha equal to 26 degree and beta equal to 35 degree. Use method of slices the analysis. Use method of slices the analysis. So this is based on slices methods how to solve these problems. Okay. Solutions. Given data, C is given 25 kN per meter square, phi is 20 degrees given, gamma is 19 kN per cubic meter. The slope is 1.5 horizontal to 1 vertical. H is given 9 meters. Directional angles are given, alpha is 26 degree and beta is 35 degree. To find factor of safety by the method of slices. Factor of safety by the method of slices. See, so last sessions we have already seen how to draw the embankments as per method of slices. Same steps are here. Draw the embankment as per data givens. Draw the embankment as per data givens. Okay, so here you select scale, so that is 1 centimeter equal to 2 meters. So 1 centimeter equal to 2 meters. Okay, so then draw the embankments, means select this concept. Okay, so here draw the horizontal line and select alpha value based on the slope value, locate the embankment, then draw the top level of the embankment with respect to height. So then locate the O point and take the radius and draw the slip circles. So then note down the theta value in radians. So then you divide number of slices based on the distance obtained from the embankment. So then calculates normal force, tangential force, self weight, area, etc. from the embankment sketch. So then now in second step, make the tables. So that is slices numbers. So you maximum slices you select 8. Then second column, it's referred as a area of slice, that is A equal to B into H. Here B is the width of each slice in meter and H is the height of each slice. Here H we are taking first slice is total height, that is 0 divided by 2. So like in second slices, average of two sides, that is H we are getting. So that is area of slice A equal to B into H in meter square. And weight of slice, that is W equal to, we are calculating area of slice into unit weight of soils in kilonewton per meter square. And normal shear stress, that is normal shear N equal to, we are calculating W cos theta in kilonewton meters. Okay, and tangential shear T we are calculating W sin theta in kilonewton per meters. So then, so like up to how many slices you have selected, so that's you complete here in this table. So then Now you do the summation of sigma n, that is we are getting 2374.89 kilonewton per meter, and summation of sigma t is 763.23 kilonewton per meter. So this value, while solving the problems, we are getting this much. Then third step, calculate length of arc L equal to r theta, where theta is in radians. So that theta we are multiplying into pi by 180, we are getting radians. So then L we are getting in meters. So then you calculate factor of safety by using the equation Fs equal to Cl plus tan phi into sigma n divided by sigma t. So we are getting value in terms of numbers. See here, factor of safety equal to C is 25 value, C is given, that is 25. L you substitute from this, plus tan phi is given 20 degree, that is angle of internal frictions, that is here phi is 20 degree, C is 25. So here C is 25, phi is 20 degree, to sigma n is 2374.89, this is 2374.89, and sigma t is 763.23. see, this is 763.23. okay, so now this value, so after calculating, now we are getting factor of safety is 2.034. so this is the complete solution of method of slices, how to calculate factor of safety. Next, third example, an embankment is inclined at an angle of 35 degree and its height is 15 meter. The angle of shearing resistance is 15 degree and the cohesion intercept is 200 kilonewton per meter square. The unit weight of soil is 18 kilonewton per cubic meter. If the Taylor stability number is 0.06, determine the factor of safety with respect to cohesion. See here this type of problem, how to solve. Given data, inclined angle is given 35 degree, H is given 15 meter, phi is given 15 degree, C is given 200 kilonewton per meter square, T is given 18 kilonewton per cubic meter, that is gamma value, 18 kilonewton per cubic meter, gamma is given. Taylor stability number Sn is given 0.06. Then to find factor of safety with respect to cohesions, Fc equal to how much? So these are the given data and what is to be required. Next, procedures. The factor of safety is given by the following equation based on this concept, Taylor stability number Sn equal to C by Fc into gamma into H. Now substitute the value in these equations. Sn is 0.06, C is 200 divided by Fc is as usual, this is required, gamma is 18 and H is 15. Now we are getting factor of safety with respect to cohesion is 12.3. This is the solutions of these problems. Now you remember only formula. Next formula, how next problem, how it's asked. A 5 meter deep canal has slopes of 1:1. The properties of soil are Cu is 20 kilonewton per meter square, phi u is 10 degree, E is 0.8, G is 2.8. If Taylor stability number is 0.108, determine the factor of safety with respect to cohesion when the canal runs full. Also find the same case of sudden drawdown if Taylor stability number for this condition is 0.137. So this is slight change. Let us see how to solve these problems. Solution, given data, H is given 5 meter, slopes is given 1:1, Cu is given 20 kilonewton per meter square, phi u is given 10 degree, stability number is given 0.8, G is given 2.8, Taylor stability number Sn is given 0.108. To find factor of safety with respect to cohesion, Fc equal to how much when the canal runs full, and in second case Fc equal to how much when the canal in sudden drawdown if Taylor stability number is 0.137. So this is the what is to be required from this problem. So now this clear data are written from the problem. This you should be required first clear. So then follow the procedures. First step in procedure, we know that gamma saturated equal to G plus E by 1 plus E into gamma W. So now we calculate first the saturated density. So substitute the value here. G is 2.8 plus Y ratio is 0.8 divided by 1 plus E is 0.8 into gamma W is unit weight of water, that is 9.81 kilonewton per cubic meter. While substituting value and while operating, we are getting 19.62 kilonewton per cubic meter. This is the saturated unit weights. So then we know that submerged unit weight equal to gamma saturated minus gamma W. So now substitute here. Gamma saturated is 19.62 minus gamma W, that is unit weight of water, is 9.81. So we are getting 9.81 kilonewton per cubic meters. So this is the density is calculated. Now case 1, factor of safety with respect to cohesion is given by the empirical equation C by Sn into gamma dash into H. Here C is 20, Sn is 0.108 into gamma dash is 9.81 into H is given in 5 meter. So answer is 3.8. Similarly, you calculate in case 2 factor of safety with respect to stability number, that is C by Sn into gamma saturated into H. So now substitute the value here. C is 20, Sn is 0.137, gamma saturated is 19.62, H is 5 meter. So we are getting factor of safety 1.5. This is with respect to gamma saturated. Next problem. An embankment is inclined at an angle of 35 degree and its height is 15 meter. The angle of shearing resistance is 15 degree and the cohesion intercept is 200 kilonewton per meter square. The unit weight of soil is 18 kilonewton per cubic meter. If the Taylor stability number is 0.06, find the factor of safety with respect to cohesions. So this is also one type of problems. Follow the same steps here. Don't make confused. Okay. Now write given data. Slope angle beta equal to 35 degree is given. H is given 15 meter. Phi is given 15 degree. C dash is given 200 kilonewton per meter square. Gamma is given 18 kilonewton per cubic meter. Taylor stability number is given 0.06. To find factor of safety with respect to cohesion, that is Fc equal to how much. Now follow the procedure. The factor of safety with respect to cohesion is given by Fc equal to C dash by Ns into gamma into H. So this equation you should be remembered. So now substitute the value in this equation. C dash is here 200, Ns is 0.06, gamma is 18 kilonewton per meter cube, that is 18, H is 15 meters, that is 15. So while operating this, we are getting the factor of safety 12.34. So this is the solution of this stuff. Here you write clear given data, what is to be required, and write the formula. We are getting answers. So within 2 to 3 minutes we are getting answers. So sometimes this problem are asked for 5 to 6 marks. Okay, but you remember the equations and write clear given data. That is the main, and operate the calculator correctly. Next problem. A homogeneous slope 15 meter height is made of C5 soil with unit weight of 18 kilonewton per cubic meter. unit cohesion 50 kPa and angle of internal friction of 25 degree. Check whether the slope is stable or not. Compute the factor of safety with respect to cohesion and critical height of slope. So this is slight different problems. Solution. Given data, here H is 15 meter, gamma is 18 kilonewton per cubic meter, C is 50 kPa means 50 kilonewton per meter square, phi is 25 degrees given. Then to find Fc equal to how much, that is factor of safety with respect to cohesion how much, and Hc critical height equal to how much. Follow the procedures. So step 1 in procedure, factor of safety with respect to cohesion is given by Fc equal to C dash by Ns into gamma h. So here substitute the value in this equation. C dash is 50 divided by Ns is 0.075 Ns. If it is not given, you assume, and gamma is 18 and h is 15. So now we are getting factor of safety with respect to cohesion is 2.46. The critical height of slope is given by the equation 3 above, that is Hc equal to C dash by Ns into gamma. So now substitute the value in this equation. C dash is 50, Ns is 0.075, gamma is 18. We are getting critical height is 37.03 meters. Then write the comment. The slope height h is 15 meter is less than the critical height 37.03 meter. Therefore, the slope is unstable. So this is the main conclusions of these problems. Next problem C. An embankment is inclined at an angle of 35 degree and its height is 15 meter. The angle of shearing resistance is 15 degree and the cohesion intercept is 40 kilonewton per meter square. The unit weight of soil is 18 kilonewton per cubic meter. Find the factor of safety with respect to cohesion. Consider Taylor stability number 0.06. Solution. Given data, beta equal to 35 degree, h is given 15 meter, phi equal to 15 degree is given, C dash is given 40 kilonewton per meter square, gamma is given 18 kilonewton per cubic meter, Taylor stability number Ns is given 0.06. Then to find factor of safety with respect to cohesion, Fc equal to how much? Procedures. The factor of safety with respect to cohesion is given by Fc equal to C dash by Ns into gamma h. So in this equation you substitute the value. C dash is 50 divided by Ns is 0.06 into gamma is 18, h is 15. Now we are getting factor of safety answer with respect to cohesion is 2.469 while operating. So these are the references or referred for module 3 of session 3 to covers in details. Okay, thank you one and all. Next class I will be continue.